Something impossible sits inside Jupiter's magnetic field. Not far from the equator, buried under thousands of kilometers of crushing hydrogen, there's a patch of magnetism that shouldn't exist. Every model of how giant planet magnetic fields work predicted a smooth, symmetric shape wrapping the whole planet. Instead, a spacecraft called Juno found a bruise in the field, a concentrated knot of magnetism so intense and so localized that after 8 years of measurements, no one has explained it. And the strangest part, it appears to be moving. When NASA's Juno spacecraft arrived at Jupiter in July 2016, it carried a magnetometer designed to do something no probe had ever attempted: map the deep interior magnetic field of a gas giant with high precision. What it found in the first few polar orbits stunned the science team. Jupiter's field wasn't smooth. It wasn't symmetric. It had structure, sharp, localized, unpredicted structure. And in the southern hemisphere, just south of the equator, one region stood out so severely from the surrounding field that the team started calling it the Great Blue Spot. Blue for the direction of the field lines, plunging inward into the planet. But that name hit a much bigger problem. Every dynamo model of how giant planets generate their magnetic fields, decades of theory refined through supercomputer simulations, had predicted this region should look nothing like what Juno was seeing. To understand why the Great Blue Spot is so strange, you have to understand where Jupiter's magnetic field comes from in the first place. Jupiter is not a solid planet. It has no crust, no rocky surface. Beneath the visible cloud tops, hydrogen gets compressed by the crushing weight of the atmosphere above it. Roughly 90% of the way toward the center, the pressure becomes so extreme that hydrogen atoms give up their electrons and start behaving like a liquid metal. This deep ocean of liquid metallic hydrogen is what generates the magnetic field. As the fluid convects, hot material rising from below, cooler material sinking, the whole thing spinning with the planet, it drags electric currents through itself. Those currents produce a magnetic field, the same basic mechanism that generates Earth's field through motion in its molten iron core. It's called a dynamo. Every large planetary magnetic field in the solar system is thought to work this way, and for decades, models based on this idea produced predictable results. Clean, dipolar fields, mostly aligned with the rotation axis, with slow, smooth variations across the surface. When Juno was designed, that was the picture nearly everyone expected to see confirmed. Juno's polar orbits let it fly closer to Jupiter's cloud tops than any spacecraft in history, at closest approach just 3,000 kilometers above the visible atmosphere. That proximity meant the magnetometer could resolve fine detail no earlier probe could see, and what it saw broke the models. The field in the northern hemisphere was intense and complex, concentrated into a bright band that looked nothing like a smooth dipole. The southern hemisphere was different, smoother overall, closer to the classical prediction. The two halves of Jupiter's magnetic field looked like they belonged to two different planets. Whatever process was generating the field wasn't behaving the same way in the north and the south, and no dynamo model had a clean explanation for why. And then sitting just south of the equator in the smoother hemisphere was the anomaly, the Great Blue Spot, a patch of magnetic flux pointing sharply into the planet, roughly the width of North America, with an intensity no smooth dynamo model produced. It looked less like a smooth feature of a global field and more like something localized had been stamped into the planet's interior. Follow-up measurements across dozens of orbits revealed something even stranger. The Great Blue Spot is drifting. Slowly but measurably, its position is shifting relative to the surrounding field, and the shape of the surrounding field is changing with it. That kind of slow change over time is called secular variation. Earth's magnetic field does it too. But Earth's dynamo isn't buried under a hydrogen ocean, and Earth's models predict the drift reasonably well. Nobody predicted Jupiter's. 3 explanations are competing to make sense of what Juno is seeing. The first is that the dynamo generating Jupiter's field doesn't sit only in the deep metallic hydrogen layer. Instead, part of it operates shallower, in a transition region where hydrogen becomes only partly ionized. Currents flowing at different depths would produce different field structures on the surface, and the Great Blue Spot could be the fingerprint of a localized, shallow current sheet. A piece of the dynamo living far above where the models assumed all the action was. The second explanation involves helium. Under Jupiter's interior conditions, helium may not stay mixed with hydrogen the way earlier models assumed. Instead, it can rain out as microscopic droplets, sinking through the liquid metallic hydrogen and forming a stable stratified layer somewhere in the middle of the planet. That kind of layer would block convection between the outer and inner regions. If it exists where the models suggest it does, it could pin certain field structures in place while letting others slowly drift above it, which is exactly what the Great Blue Spot looks like it's doing. The third possibility is the least comfortable, that the dynamo physics itself needs to be revised at Jupiter's conditions. Standard models rely on assumptions about how convecting fluid averages out local structure. If those assumptions fail inside a planet like Jupiter, the models are wrong at a level nobody has worked out yet. Juno is still flying. Its extended mission has added years of measurements, and each new orbit sharpens the picture of how the Great Blue Spot is moving and how the rest of the field is changing with it. Somewhere below those clouds, physics we don't yet fully understand is drawing shapes on the inside of a gas giant. And every reading Juno sends back gets us closer to naming what it is. Whatever is making that mark, we haven't seen it anywhere else in the solar system. If you like this one, hit subscribe. There's more strangeness where this came from.